So far we looked into a constant demand profile, we looked into constant demand profile, constant demand profile. That is what we looked into. But in reality this may not be constant, it might vary. There can be seasonal variation, there can be varieties of variation. For example, you consider a hotel, right. So, seasonal variation would be there, even hospitals, there can be seasonal variation of any one of the resources that you finally want to supply. For example, even the situations are quite different of course, but let us say oxygen storage, how many cylinders you should be keeping, right, all right. But the variable supply could be variable, where we have continuously requirement over 24 hours, it can vary in certain manner, right. So, the variable demand one should actually consider, variable demand one should consider, and variable demand one can look into, and this variable demand quite often it might exhibit a kind of, if it is more of the random type, then it might show normal distribution, normally distributed population actually. So, demand will vary usually normal distribution. Now, I just to recollect your good old days, when you have got good old days statistics a little bit, when you have too many variables, too many factors affecting the variable. In other words, if a random variable, if a random variable is sum of several random variable, maybe k1, x1, etc., in that case is likely to vary normally. When there are infinite number of them, likely to vary normally, in the sense that you will have this sort of a bell shaped distribution, right. It's very simple to understand from arguments and logic. For example, very simply, supposing I have again situation of a die, so I have 6 outcomes possible, 6 possible outcomes, 1, 2, 3, 4, 5, 6 outcome possible, right, and probability is uniform. So, it is uniform distribution, because everyone has got a probability of. So, if you do 1000 times, you will find 1/6 of the time it will be 1, in the long, or 6000 times, 1000 times, 1000. But if I have 2 such die, I have increased the factor, not 1 die now, 2. So, my variation would be now going from 2 to 12, spread increases, 2 factors. Now, how can simply 2, how can you get 2? 1 from each of them. So, if you calculate out the, what are the possibilities? Possibilities are 1, 1. So, if you calculate these possibilities, joint probability of finding 1 in both of them. So, 1 by 36, there are 36 possibilities now. Keep 1, 6 possibilities from the second one, 2, so 36 possibilities. So, this is simply 1 by 36. What about 3? 2 by 36. How? Because 3 I can get 1 from the first one, 2 from the second one, or 2 from the first one, 1 from the second one. So, there are so 2 out of 36. So, the third one would be 4, let us say 4 I can get 1, 3, 2, 2 and 3, 1. So, it would be simply, one could have done from Bayes theorem, joint conditional probability, that first one is 1, what is the probability of finding, but I think I am simply trying to explain you. So, you will find that it actually linearly goes like this, and 12, how can you find it? 12 will be 6 6 from both. So, therefore, it will be something like this. You can actually do this exercise and you can find a little bit triangular, which this 7 would be, 7 would be somewhere there, 7 would be there, right. Now, if you take 3 die, then the spread increases from 3 to 18, spread will increase, and you will find that it is no longer linear, but it tends to be curvilinear. And when you have infinite number of dice, let us say, or infinite number of factors, then the spread is very large. In fact, it is from minus infinity to plus infinity ideally, with a 0 mean you can actually do axis shift and all that, and this is a curvature of this kind. So, that is the whole idea. So, e to the power minus u square, etc., etc., the formula that you have for normal distribution, Gaussian distribution. So, when you have too many factors affecting the random variable, it is normally distributed, and we assume that standard normal variate of course go from minus infinity to plus infinity, and these parameters are the mean, which is 7, it was a 14 plus 12 plus 2 divided by 12 plus 2 was 14. So, the mean, the central tendency where it will have the peak, thus like you have got 3 parameters, what we call the mean, median and mode. So, mode value is same as arithmetic average, what is called as a measure of central tendency or mean. So, mean is nothing, mean can be calculated as arithmetic average. So, if I have standard normal variate, if I take its mean as 0, because its spread will go on both the sides, right. So, you will have something. So, and this is bearing within, then we define something called standard deviation. Why? Deviations I could have found out, but sum total of the deviations will be 0. Therefore, what we do, you find out x minus mu or x bar or whatever you call it. If it is for sample, you do it like this, sum it up, sigma of all this divided by total number of them if the sample size is large from where you have measured, with the otherwise n minus 1, etc., etc. So, you can find out standard deviation, this is nothing but s square, it will be n minus 1, or if it is large number of values you are doing for all the whole population, then you will possibly denote by mean, and this would be sigma square, or sigma is equals to under root, root means square deviation in a way. So, this is 3 sigma, this is minus, this side is also 3 times sigma, because now I have normalized everything. So, standard deviation is also normalized, because I would have divided this standard, if I take this as 1. So, this will be plus 3 and minus 3. So, I do not think I will go further into this, but where you have too many factors affecting your demand, then it will be normally distributed, right, normally distributed. So, many cases you will find in engineering situations or even science, where things are variation depends upon too many factors, right, too many factors. So, for example, for like our variation of properties of material which we measure, let us say properties of asphalt in pavement or properties of concrete, these are all we assume normally distributed, because too many factors would be affecting the properties. So, if we know several demand profile from the past, right, their optimal storage and supply, for each one of them we can find out several, so optimal storage and supply, we can find out the optimal combination, right. So, we can actually find out, and they are likely to be normally distributed finally, and then you find out the expected cost, where probability of failure, for example, you found out that this is the this, if your supply is more than that, if your supply is more than that, the basically difference between, basically the demand varies in this manner, and corresponding supply, supposing it is more than that, more than this value, most of the time, this time it will be satisfying, and if my supply is somewhere here, this time it will be satisfying, this it may not satisfy. You keep it in such a manner. Let us say this is your demand, average demand profile or optimal demand profile, something you say. So, you can maintain your supply at such level in certain cases. I will just give you an example, where if you might like to satisfy the demand most of the time, but take a little bit of risk also. So, this is the probability of failure, this area under this curve, and this is 1 minus that is the probability of not failure or success, I will say. So, if you know the cost of failure, probability of failure is known, this is cost of satisfying that demand, if you know, then expected cost you can find out, right, and then choose basically corresponding supply value or corresponding supply and storage value or whatever it is. So, this is what. So, given set of storage and supply satisfy there are several demands, out of which possibly if I cumulate them or get their distribution, say average demand or total cumulative demand, something like that. If we can I can use these concepts also to find out which is the best, but this becomes simpler if I can find out the cost of failure. So, this becomes simpler. For example, in a case like, let us say this, simply something like this, consumption of oil. Let us say I am using furnace oil for heating my boiler. This is today of course you might have other options. Consumption of oil for your hot water supply. So, you are using furnace oil. Now, you have done a lot of observations and you found that this is the histogram plot. So, this is the number of times you had between 0 to 5, this 0 to 5 liters requirement is this much, 5 to 10 liter requirements, this is the frequencies, this is the frequency F1, F2, etc., etc. So, relative frequency you can talk of, if you divide by the sum total of all the frequencies you will get relative frequencies. So, relative frequency curve you can join it by a smooth line. Now, supposing you keep your oil capacity to 30 liters, you will be satisfying all the time. You keep 30 liters, you will be satisfying all these demands, but you will be missing out on these demands, you will be missing out on this one. So, your probability of failure is given by the area under this curve. If you have done relative cumulative frequency, relative frequency, if you have written Fi F1 divided by sigma F, Fi divided by sigma Fi, that gives me relative frequency. So, area under the curve then will be equals to 1, because this is some fraction, this is some fraction, and sum total of all these fractions will be equals to 1. So, the area under this curve, if I join by a smooth curve, will be equals to 1, relative frequency distribution, relative frequency. So, this is the probability of failure and this is the probability of success if I maintain 30 liters capacity or 30 into 30 kiloliters capacity. So, this is the probability of failure, but then cost of this failure I might lose out on my customer, or I might lose out on, supposing it is a hotel or something of that kind, I might lose out on my customer, or maybe I have to pay some penalty. So, cost of failure can be estimated in that manner, that you are either so cost of failure can be estimated in that manner, either you are losing a customer on the overall because you do not supply regularly, you are not satisfying your customer, or might have to pay penalty. And but for satisfying this I have to keep higher storage capacity, highest inventory has to be higher, storage capacity would be higher, and therefore, there is a cost involved. Higher, as I go on increasing, this cost will be increased. So, you find out same probability of failure multiplied by the indirect cost of failure. Maybe there are some cases direct cost of failure also could be there, and this is the direct cost of satisfying the requirement. So, this is how one can actually determine, right. So, this is how it is shown. same the relative frequency diagram, and this is I am saying 3 sigma minus 3 sigma. So, you can find out in this manner. So, you can plot actually probability of failure versus capacity. Now, probability of failure will be simply this areas, like as I said, this areas, right. So, probability of failure would actually as you increase the capacity, storage capacity of your tank, probability of failure will reduce down, right, probability of failure will reduce down, and you can find out. So, that is how we do handle in some situations. Then in some other situations, for example, I was talking about the hotel room, right. Now, one is seasonal variations. For example, just in many of the hotels in India, let us say their their main customers are from Western world. So, large chunk of them come during the winter time, December time, and go back before the Christmas and things like that. So, this is seasonal variation, that you can that seasonal variation you can plot over the season or know over the season, and then accordingly that would go into your variable demand profile. For example, you also know if hotels, I am giving an example, there is a tourist seasons for most of the places. Say I will give you example, it is known that people from, let us say, during certain religious time, religious festival, Navratri time, people from Gujarat go for parikramas, right. So, hotel demands will go accordingly. Similarly, people during almost October time, a lot of people travel from Bengal, and people like to travel to south from north during winter period. No, people would not prefer to go to, let us say, Kerala during monsoon season, it is too much of rain, you can't travel. So, hotel scenarios, they can actually find out seasonal variation and demand profile for several, you can actually, if you are looking at this. But this is one thing. The other thing is how much I should actually, say I want to size the hot water supply system for hotel, let us say, I am showing the extreme case, or for hospital intensive care unit, oxygen supply units I need. Now, you will find that there is a diversity of usage, in the sense that if you have 100 rooms, all 100 rooms are unlikely to be occupied all the time, only some fractions will be occupied based on, because you might have made your capacity of 100 rooms hotel, 100 rooms, assuming an overall kind of a, overall kind of your resources and things like that. So, looking at the overall business scenario and overall kind of things like that, but all rooms will not be occupied all the time. So, if you are doing sizing for your hot water supply system, you need not do for all 100 rooms. Outlets will be there in all 100 rooms, but the line that is supplying to 100 rooms need not be meant for all 100 rooms. You can multiply by a factor called diversity factor, because diversity of usage, everything are not used simultaneously. For example, all classrooms will not be used simultaneously in a lecture hall complex. So, you have to, if I have to supply the power line, and each one, let us say, requires, the maximum demand is, let us say, 15 ampere or 32 ampere. Now, the pipe, the line, I mean not pipe, the power line which will actually be connected to all the rooms, that need not be 32 multiplied by number of rooms, it will be multiplied by a factor. That factor we call as diversity factor, that factor we call as a diversity. So, if you have a hotel with 100 beds, the example is given, we want to provide central air conditioning system, let us say. If there are n 50 and or another case, let us say there are 50 outlets of 15 amperes, we need to size the electric lines, we need in this first case I need x turns of AC, which will be less than 100 multiplied by for a given room, because all 100 rooms will not be occupied simultaneously. This is called, so there is a multiplication factor, that factor we call as diversity factor. But for in the design services we do not design for full load, but for partial load depending on the satisfaction level. If you provide for all 100 rooms, you will satisfy all the time, no risk you have taken. But supposing you decide to satisfy for some 50 or 60, then you will satisfy the simultaneous demand for certain proportion of the simultaneous demand. If it exceeds, you will say, oh, I do not have an AC room now. So your customer might run away or maybe there, but you have to decide there whether, but satisfying all 100 will be too costly for you, because many of them, this sizing would be too large and it will not be worth, or many of them will not be used together. So this is the partial load expressed as a percentage of total load is called diversity factor. And what we do is, how do I find it out? I must have some past data available to me, something should be known to me. So supposing I have got n outlets or n rooms, AC rooms, and I have gone 1000 times there. That is the example I am giving, or it is not 1000, I have just recorded. I mean, we should record it actually, you should be recording it, building services system or maintenance system, that makes it more scientific, which we normally is not a very good, it is not a practice in India, but supposing this record is available to you, all records of how many people actually occupied the building in a similar type of building, because in the new building if you are doing, then for the new building data will not be available, but the past similar building if you have data available, and data is available means for last 5-6 years data you got, and let us say there are 1000 such data, how many have been used, how many room was in use, then you will find that if I have 1000 such data, I can plot a histogram of frequency of use on this axis and number of rooms on this axis, number of rooms, right, this axis, number of rooms in this axis. So 0 to 10, 10 to 20 up to 100, let us say 100 rooms I am talking of, up to 100, and then this I call as F1, this I call as F2, etc., etc. Let us say, let me use another color, F3, F4 and so on and so forth. So this is frequencies, and I can now, this is frequencies, and sum total of this frequency will be how much? Sum of all Fi, because I have gone 1000 data is available to me, I have just said, so this will be equals to 1000. And this F divided by 1000, this I call as relative frequency, which will be a fraction, and sum total of all relative frequency, that is sum total of Fi divided by sigma Fi is equals to 1, because each one of them will be, right. So Fi, F1 by sigma Fi, F2 by sigma Fi, if I sum them up they will be equals to 1. So area under this curve is 1, that is a histogram plot for relative frequency. So if I know this, then I can find out mean number of rooms in its use, mean number of rooms, right. What that would be? That will be simply F1 multiplied by sigma Fi, sum total of sigma Fi, basically this, how do I find out? The value of the random variable multiplied by its relative frequency. So if I know this average will be not F1, this value is 5, this value is 15, I am taking the class, the central point in the class interval or average of the class interval. So 5 into F1 divided by sigma Fi plus 10 into, so this would be, the mean is given as, simply given as, let me just write it down, xi sigma Fi, I mean Fi sigma Fi, that is right. So sigma of all this I going from 1 to whatever the value is. So that is the mean, that is how we find out the value of the random variable multiplied by the relative frequency or the probability. If you sum that up, that gives you expected value or the mean. So I can find out the mean number of rooms that was in use. Now, I had 100 rooms, out of this mean number of rooms that was used given by this. Let me call this as n, let me just call this as n number of rooms on an average I found was in use. So, n divided by 100 will be the probability of finding one room in use on an average, probability of finding one room in use at any point of time, right. So, this is how I can obtain probability of finding. So, this is the histogram, number of bedrooms in simultaneous use. I mean one room, I found 0 to 10 room, I did not find any time. It was a good case 10 to 20, right, and so on so forth. That is how I find out. So, if I find out, then I can find out mean number of rooms in use. This divided by 100 gives me probability of finding only one room in use, that I call as probability of success. Like we did in lift, we will call it probability of success. So, mean number of room is in use, that is what I have just now given you the formula, x bar I am calling it, right, sigma fi xi divided by sigma fi, and probability of finding one room in use will be given by x bar divided by n, where n is 100 in my case, x bar is the mean number. So, probability of, right. So, probability of finding only one room in use out of say 60 room, only one room in use is a binomial distribution, because probability of success now one room in use is given by this probability of success, 1 minus p is probability of failure or not success, no room in use. So, this how probability of finding 0 room in use is given by MC0, which we have done earlier, we have discussed this earlier sometime, right, in connection with, we discussed this binomial distribution, just in connection with the lift we discussed when we were talking of Poisson's distribution. So, MC1 probability of finding only one room in use and m rooms are not in use, m minus 1 rooms are not in use is this. Now, if you find out, so probability of 0 room in use, probability of 1 room is in use, probability of 2 room is used and 8 is not in use. If I sum this up, all sum total will make it equals to 1, because possibilities are no room in use, 1 room in use, or 2 rooms are used simultaneously, or 3 rooms are used simultaneously, or all m rooms are used simultaneously. So, these are the all outcomes possible. Sum total of this outcome will be equals to 1, and if you sum this up, they will obviously, you can show that algebraically, that comes out to be 1. Now, you go on adding this up, supposing I provide only for one room, my let us say ducts, AC ducts, I have 100 room capacity, I provide for only one room, I will satisfy only this much percentage of my 100% simultaneous demand. 100% simultaneous demand corresponds to all m room being supplied. If I supply less, certain percentage of the time I will not be able to satisfy the simultaneous demand of all rooms. So, this sum will give me some percentage or fraction, because sum total of Pi, this P0 which is equals to P0 plus P1 plus this is equals to 1, 100% up to m, right. But you find out that probability of m room being used is relatively less, that you can see from this diagram. You see this becomes less, this is not as high, whereas up to this is pretty high. So, I can possibly supply up to 80 rooms and take risk of this much, right, but that will be a managerial decision, how much risk I want to take, all right, how much risk I want to take. So, this I can sum this up, and all sum will be equals to dot 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 dot, it will be equals to 1, and I have to take a decision that how much risk I want to take. Let us say I decide 90% satisfaction, 10% risk I will take. So, I go on summing them up, and at some value of p, let us say p y, this value will correspond to 0.9. Then y is the number of rooms to which I will cater my pipelining or everything, such that I am taking 10% risk, because y corresponds to 0.9.